On the next slide here, we're talking about section 1.2. So we've just transitioned sections, and we have a goal here to be able to graph and order real numbers. And so also to be able to identify properties of real numbers. So two different goals. First, you've probably seen this figure before, this Venn diagram, which helps us to consider all of the different groups of numbers. First, we have the natural numbers, and those are counting numbers. Those are the first numbers you talk about in kindergarten. And we use an N to represent natural numbers. The next set we learn about 0 is whole numbers. So that's a W for whole numbers, and all of the whole numbers, the natural numbers, are all included within the whole numbers. And then we learn about integers, and for integers we actually use the letter Z. We reserve I for something else later. So we're using Z, and that includes our negative numbers, our whole numbers, and 0. Next are irrational numbers, and those are numbers, we actually use the letter Q, and the Q actually stands for quotient. So those are numbers that can be written as a fraction. All of these numbers can be written as a fraction. And of course all of these numbers and these can also be written as a fraction if we simply put them over 1. And then on the other side of the Venn diagram are the irrational numbers. You notice there's not overlap in those two sections. Irrational numbers are numbers that do not terminate and do not repeat. So maybe make a note of that. Do not terminate, meaning they do not end. There is no end to the decimals here. Do not terminate and do not repeat. There's no pattern as there is here in the 0.2 repeating. So rational numbers are all numbers you can write as a quotient of integers, A over B, where B does not equal 0. They include terminating decimals, such as 1/8 or 0.125. And they include repeating decimals. For example, 1/3 can be written as 0.3 repeating. For irrational numbers, they have decimal representations that neither terminate nor repeat. So there that is again. For example, the square root of 2. The square root of any number that is not a perfect square will lead to an irrational number. And they cannot be written as the quotient of integers. So for example, your school is sponsoring a charity race. Which set of numbers does not contain the number of people P who participate in the race? And the number of people that participate in the race could be a natural number, because that includes, we obviously would need a positive number, or 0. So integers include those options. Rational numbers, so again, since integers and whole numbers are included within rational numbers, then of course we could find those values in rational numbers, the set of rational numbers, but not in the set of irrational numbers. Example 2, graph the numbers. So we're going to draw a number line. Looking at these values, -5/2. Sometimes it's easier to write them as a decimal, so we're going to write -5/2 as -2.5. The square root of 2 you can simply enter into your calculator, and you get, let's see, the square root of 2 is 1.4. And then 2.6 repeating, and that's already written as a decimal. So we can go ahead, on our graph we need to go down to -3 and up to +3. And fill in the rest. And then we plot our points. -5/2 would be right here between -2 and -3. And we're going to go back and write them in their initial form when we graph them. And the square root of 2 is 1.4, so we'd find that here. Oops, square root of 2. And 2.6 repeating is just past halfway between 2 and 3, so the 2.6 repeating. Next we compare the square root of 17, which would be an irrational number since 17 is not a perfect square, and 3.8. So One easy way to do that would be to think about, well, what is close to the square root of 17 that is a perfect square, and that would be the square root of 16. So the square root of 16 we know is 4. And we know the square root of 15 is greater than, or sorry, the square root of 17 would be even greater than the square root of 16. Since 4 is greater than 3.8, we therefore know that the square root of 17 would be greater than 3.8 as well. You could also enter into your calculator to double check the square root of 17 equals approximately, I'm going to use my squiggle lines for my equal sign to represent approximately equal to. So square root of 17 is approximately equal to 4.123, which of course also is a greater than 3.8. And our last page. Here we have our different properties for real numbers, starting with the opposite or additive inverse of any number A is negative A. So that's our phrase additive inverse we should be familiar with. The sum of a number and its opposite is 0. So the additive identity would be adding two numbers together and getting 0. Next we talk about the terms reciprocal, or also known as the multiplicative inverse of any non-zero number. A is 1 over A. So for example, we can see that 8 and 1/8 are multiplicative inverses or reciprocals. And we also know that the product of a number and its reciprocal is always 1. And that comes in handy. These all come in handy as we're solving algebraic expressions. You can take a look at the chart here, and we have some other properties. The closure property here is represented by A plus B is a real number, and the multiplication version of the closure property would be A times B is a real number. Next, the commutative property, and think of the word commute here, and that is when we have two values that can switch places when we add them or multiply them and get the same result. The associative property, think about who you associate with, so who you are grouped with. In this property we see A plus B, the group, plus C is going to be equal to A plus the group B plus C. Notice that the order is the same, the groups have just changed, and this also applies in multiplication. Next is the identity property. So for addition, our additive identity is 0. So if we add 0, we still get the same result. For multiplication, 1 is the multiplicative identity. So anything times 1, it has that same result. Next is the inverse property, and so we have what we talked about a little bit above, which is when we add a number plus its opposite, we get 0. And when we multiply a number times its reciprocal or multiplicative inverse, we get 1. And of course, A cannot be 0. That would make the denominator 0. And lastly, the distributive property. And the distributive property is when we have a value outside of parentheses with an operation happening, addition or subtraction within the parentheses, we distribute the value outside. So A times B is AB, and A times C is AC. Which property does this equation illustrate? So we have some examples here. So we have negative 2/3 times negative 3/2 is 1. So that's your multiplicative inverse. This one's tricky a little bit because you see the parentheses, so you may want to think about associative property, or you may want to think about distributive property, but actually notice that the order is different on both sides, and therefore this is actually representing the commutative property of multiplication. And lastly, we have 3 outside parentheses, g plus h plus 2g. And now, in the result, we have 3g plus 3h plus 2g. The 2g stays the same, so what's different? Well, the distributive property happened. So we'll label that distributive.